we are given that there is a single integer solution, okay, to this quadratic with unusually large constant term. Now, common approach here would be to use the quadratic formula, but notice that the discriminant here would be what? 7 squared, okay, plus, because there's a minus sign right here, plus 4 times 105. Now, I'm just showing you the enormity of the discriminant. And of course, it would be no fun to just cheat and use a calculator, right? If you want to do that, go right ahead, but it's not something that we're interested in terms of a challenge here. Okay. So folks, let me just make sure the context is here on this. This would be the square root portion of the quadratic formula. Okay, again, b squared minus 4ac, but there's already a minus right here, so that's why this becomes a plus. This 4 is part of the formula. 105 is the coefficient right here. And so you can see how large this would be. Now you're given that this is an integer, that there is an integer solution, so you would anticipate this rationalize, or this resolving to an integer or a rational number. But it's just way too much computation here, right, folks? 4 times 105 times a 5-digit number. We're talking about a radicand here, or a discriminant, in the tens of millions, okay? So that an approach would be to do that, and then see if you could figure out what if you know, it will be a perfect square, and what that integer would be that you would have to square. Also, trying to factor this by grouping is another approach that I tried. Very painful, or maybe a nice way of doing that. I want to show you another approach here that I sort of discovered on my own. I'm sure it's been around, but it's just something I noticed on my own. So I wanted to share it with you. So we can rewrite this like this just by bringing the 5534 over, right? Now, something else that's useful here is to consider the prime factorization of the constant term, okay? Now notice that it's definitely divisible by, whoops, where am I here? It's divisible by 2 clearly, because it ends in, it's an even number, right? Now the sum of the digits tells us that it, and I'll just slash through this, folks, it's not divisible by 3. And again, you know that because you sum the digits here, you get 12 plus 3 is 15, 20, 25, which is not a multiple of 3, okay? And also, it's not divisible by 5. It doesn't end in 5. Now, there's a divisibility test for 7 that I'll take the time to show you, because again, first of all, we know that 2 is in the prime factorization, and we know that 3 and 5 are not. So we're making some progress here. Again, y'all, our approach here is quite different. We're not going to use the quadratic formula. We're not going to factor it because that's too hard. We're going to use the prime factorization to solve this problem. Okay. Now, there's a kind of a fairly, I don't know if it's well known, but what you can do right here to determine if this is divisible by 7 is take 2 times the last, and I proved that on a video on this channel. Take 2 times the last digit, which is 8, and subtract it from the entire number. Well, when you do that, you get 5, 5, 3, 0, right? Again, y'all, what's the algorithm here? To test for divisibility by 7, again, we've already tested for 2, 3, and 5, right? Okay, to test for divisibility by 7, you take the last digit, multiply it by 2, and then subtract it from the number. That's what I did. 2 times 4 is 8. Subtract 8 from 8, and you get the 0 that you see right here. But notice that this is actually equal to, where are we, right here? This is equal to 7. Now, let's see, it's times what, 790? Notice that 7 times 80 is 560, right? So this would be 7 times, let's see, 5 times 7, 35. 7 times 79 is 4963. So this would be 7 times 790, okay? So this test shows that 7 is a factor of this, okay? Now the rest of it is just hard work, folks. So we determined by these tests that 2 and 7 are divisors, and then with more computations will reveal that 55,384 is equal to 2 cubed times 7 times 23 times 43. And so there's a lot of computation involved here. Getting 2 and 7 out of the way makes these numbers easier to figure out. I didn't show all the work, but we did show that 2 and 7 were divisors. And then when you do the arithmetic on that, you're going to get 23 and 43 as divisors. So this is the prime factorization of our constant term. And then notice how we factored the left-hand side here. And good news, folks, 7 appears on this side as a common factor, and 7 appears in the prime factorization, right? So what happens is we get an immediate benefit from that by dividing through by 7. And we have this situation here, folks, where we have x times the product 15x minus 1. One way of thinking about this is one factor is approximately 15 times larger than the other integer factor, okay? Now let's just take a look at some possibilities here. And again, the approach here is to realize one thing to notice right now is that let me erase that. You have 4 times 2 equals to 16 divisors. So that's not as many as you might think. That would correspond to 8 divisor pairs. Where do we get that? Well, you increment the 3, you increment the understood 1 right here, multiply them together because you have to allow for the exponent of 0. And so there's 16 divisors, and I'm going to go through and just check the conspicuous ones first, okay? So my first check will be for x is equal to 2/3, which is the divisor manifestly, right? Now, so what I'm going to check right here, folks, would be 8, okay? And then 15 times 8 is 120, so this would be 8 times 119. Right, folks? And again, y'all, I just checked for 2 cubed, okay, is a potential divisor. And I put the 2 cubed right here and got 8. I put 2 cubed right here and got 8 times 15, which is 8 times 119, right? Well, that's clearly not the same thing as this, right? 8 times 119, there's no way, right? Now, you would get a 7 out of this. What is this? 7 times 17 right here? So you see, you can, if you want to, you're not having to do too many computations, actually. 7 times 17 is 119, but none of these factors, you don't see a 23 or a 43. So you see, you have to, this doesn't work. You can X that out, right? Okay, it does not work, okay? So let's look at the next one, 23. Now, y'all, again, I'm just marching through, picking out the obvious ones, okay? We've just checked out, the ones that are conspicuous divisors. There's other divisors other than what I'm showing you right here, but these are just the ones that are the most conspicuous. So let's go ahead and put 23 in. Now notice right here, you would get 23 just in your first position, okay? Now 15 times 23, 20 times 15 is 300. Plus 45 is 345 minus 1. That would make this 344. Okay? 344. Okay? Now, if you divide this by 2 3 times, you'll end up getting 23. And again, leaving out just a little bit of the work right here. But you'll end up with 23. And 2 divides into this. Again, I don't want to waste the time going through it. But it divides it... let's see, 3 times, so it's 2 cubed, 23 times 2 cubed, and that's 8, and 8 times 43 is this number, which is not hard to do in mental math, right? So we get 43. Well, guess what? That's exactly the right-hand side, right? That's exactly the right-hand side without having to do too much mental math, all right? And so we have actually shown that x equals 23 is a solution. And there's zero reason to check it in the original question, right? Because all the computation that we did, the main computation we did was compute the prime factorization, which I left out some of the details. We got started, but then there's some more work you would have to do to figure out that 23 and 43 were the other divisors. It's just doing long division, basically, and I left that work out, okay? But x equals 23 is the integer solution. And the triumph of this method, it seems like a lot of work, and maybe you're saying, well, why did you do it that way? Well, okay, if you don't like doing it that way, try to do it the conventional way. And the only real way to do this is maybe consider completing the square, using the quadratic formula, which was this piece right here, or trying to factor by grouping. All of those are very difficult. I spent a lot of time on it, okay? So anyway, this integer solution to this is x equals 23, okay? And it's a new way to solve something like this. It's probably not new. I'm sure it's something people have thought of somewhere along the way. But in school, you're kind of brainwashed into thinking, well, you either have to factor, use the quadratic formula, or complete the square. We didn't do any of that. We didn't do any of that at all. All we did was find the prime factorization of the constant term, okay? And then it was convenient. It worked out because you had a common factor of 7. And then so you cancel those factors, and there's not really a whole lot to check, okay? Now you may say maybe there's others. Well, there can only be one other since it's quadratic form, and you were given that there was a single integer solution, is what these instructions were intended to convey, okay? So again, let me know what you think about the process. Somewhere you got to pay the piper, but here, believe it or not, in my opinion, this method is easier in my view than trying to figure out if this huge number is a perfect square. Now the steps would be, of course, multiply this out, right? Multiply all this out, and you can presume that it's going to either be a rational number or an integer because you're given there is an integer solution, but you still have to figure out what that perfect square is for a number that's in the tens of millions range. Okay, you still have to figure that out. The other approach is a factoring by grouping, try to split this stuff apart. I made some minor progress on that, okay, but it's still very difficult, I think, to try to factor this by grouping. So let me, again, if any of you guys see any tricks, but the big problem is this is a 5-digit constant here, okay, so that's tough all by itself. And then you have to multiply it by 4 times 105 to get this huge radicand, okay? So again, let me know if I'm overlooking anything in terms of the computational complexity, because I don't think the way I did this is particularly difficult. Now, you may be saying, well, you just got lucky and ran into 23. Well, you're right, because there could have been there's other potential divisors, right? Like 46 times 2 times 43, you know, or 112 times 2 times let's see, is it 112? Yeah, 112 times 2 times 43. There were other tries, but you also knew that the ratio of the two solutions is approximately 15, right? 15x minus 1 divided by x is approximately 15, right? So you look for a solution that's about 15 times larger than, and you guys can check that right here. You can see that 8 times 43 is what? 324 divided by 23 is very close to 15, okay? If other combinations wouldn't yield that, wouldn't yield that precisely. I mean, if you tried to come up with other divisors, another possibility would be 86 times 4 times 23, right? Well, you wouldn't get a ratio that was anywhere near 15, I don't think, if you tried those divisors, okay? So again, you get some information from the nature of this factorization with respect to how the two values are related to each other with respect to magnitude. But anyway, this is it. X equals 23. Let me know what you thought.